Let's take a look now at example 5 and see why exactly it's so powerful to come across an odd function that we're integrating specifically on an interval from a negative value to a positive of the same value. So what we'll see here is that in example 5, we're working with a function of f of x is the tangent of x over 1 plus x squared plus x to the fourth. And this is a rather complicated looking function. But the first thing that we should note is, or I guess I should rephrase that. We note that f of x, which is equal to that tangent of x over our 1 plus x squared plus x to the fourth, is indeed going to be continuous on the interval from -1 to +1. My tangent function is only going to become discontinuous at something like pi over 2, and that's going to be up at like 1.5-ish, so I don't have any issues with my tangent. Negative pi over 2 would also be a problem, but I'm not going down to negative pi over 2. That'd be like negative 1.5-ish. And I can see that my denominator here, the smallest it could ever be, is the value of 1. Since these values of x are being squared or raised to the fourth, they have an even power, so they always generate 0 or larger. So since I have that this is continuous on the interval, we can use the fundamental theorem of calculus part 2 to try to help us with this. Now what we're going to find here is that since again I have an interval from -1 to 1, there's a chance I might be able to save myself some time here, because thinking about how to integrate this function by finding antiderivatives may seem rather difficult, right? Like, what am I going to do? This isn't a derivative rule that I know, and it's really hard to come up with algebraic ways to simplify this, and it's also difficult to even think about a u substitution. So I might be able to see here that we can also note that if we were to go ahead and plug in negative x into our function, notice that this would look like a tangent of negative x over 1 plus a negative x being squared plus a negative x being raised to the fourth power. Now, this denominator is going to be very simple to simplify, because when I take negative x times negative x, I just get x squared. When I take negative x times itself 4 times in a row, I still end up with a positive. The weird part is thinking about this tangent of a negative x. Really quickly over here on the side, I'm going to go ahead and just explore what's going to be happening with this. Notice that if I'm working with a tangent of a negative x, I should be able to first see that this is the same as the sine of a negative x over the cosine of a negative x. And what is this equal to? Well, I can see with a little more investigation that if I was to think about the unit circle, and if I thought about working with an angle of x, let's say something like this, versus an angle of negative x, what I could see is that I'm going to be generating these points here on the circle. Now, the x-coordinates of these points, I can tell, are going to be exactly the same. They should be above each other, since on one I only rotated up and the other I rotated down the same amount. However, the y values are going to be different, because one of the y values will be positive and the other will be negative. So what this tells me is that the sine of the negative angle is going to produce the sine of the positive angle. It produces the same y, but with a negative on it. Whereas the cosine is going to be producing the same exact value as the regular cosine of negative x. It's going to be producing the same x output as the cosine of x itself. So what this tells me then is that the tangent of a negative input is really going to end up being the tangent, or I could see here the negative tangent of x. So this makes the tangent function an odd function. And that means that the tangent of negative x is equal to negative tangent x. And from this, I can see that this is actually the same thing as my original function that I had at the start, but just actually being multiplied by a negative. And so this tells me that my whole function here is an odd function. So f of x is odd, and therefore, if I'm ever integrating an odd function on an interval from -a to a, no matter what a is, I'm going to end up with the final value of immediately 0. And so notice here how much time we've actually been able to save by tackling this by using odd functions. Since this was an odd function, I could avoid doing any weird algebra manipulations, doing any sort of u substitutions, and I can just immediately arrive at a value of 0. So integrating with odd functions saves a lot more time than integrating with even functions. And again, you know this is at least an option to be on the lookout for whenever you come across an interval that goes from negative a to a. So now when we think about that list of integration techniques, and I'll summarize it down here one final time, but our integration techniques that we have so far are 1. Use derivative rules in reverse. Use derivative rules in reverse. This is what we're always attempting to push for. We have 2, which is algebra, which now contains so many different things. Splitting of fractions, doing some factoring, combining stuff, using trig identities, even being on the lookout for symmetry would fall underneath this kind of algebra step here. And then, of course, we have, finally, u substitutions. Now this list is by no means complete. In fact, if you were to move on to Calculus 2 again, this list would continue to grow to a list size of about 10 different items that are at least main topics within the calculus sequence. But for Calc 1, these are the important techniques that we have and that we need to be aware of. Of course, the best way to get good at this is to practice, and I have so much practice here on u substitutions. We have multiple different worksheets that kind of summarize all of integration as well as kind of focus very specifically on u subs, and so you can go and take a look at those worksheets and practice almost ad nauseum to make sure that you are really solid on this. When it comes to the first day of Calculus 2, you want to make sure that you're the student in the room that knows how to integrate. You know your integration techniques, you know how to do a u-sub, because that way you can hit the ground running and learn the new content even more successfully.